Marker and smartboard. A student moves a marker over the surface of a smartboard. The position of the marker is given in terms of unit vectors, right here. Okay, so you have a component in the I direction and a component in the J direction. So it's a two-dimensional whiteboard, smartboard. So find the magnitude direction of the average velocity of the marker between t equals 0, t equals 2 seconds. Then find the instantaneous velocity at various times. Then find the magnitude and direction of the instantaneous acceleration at 4 seconds, and does it change with time? Is it a function of time? D, sketch the marker's trajectory. And E, find the angle between the displacement and acceleration vectors at 4 seconds. Find the magnitude and direction of the average velocity of the marker between t equals 0 and t equals 2 seconds. First thing we're going to do is get rid of the units from the coefficients to make it easier to deal with. Later on we can put the correct units back in if we'd like. Now we have a choice of two equations for the average velocity. One is the displacement or change in position over time. The other average velocity is you add the initial and final velocity and divide by 2. Are there any restrictions on using either one of these? Yes. The second equation, this one here, requires that the object has a constant acceleration. The first equation always applies, that's the definition. Let's see if we can use the second equation by finding the second derivative of the position. So over here we have the velocity, that's the first derivative. So we take the first derivative and we get, let's see, we get 0.60 ti plus 0.50 j hat and I hat. Take the derivative again to find the acceleration, and we get 0.6 I. That's a constant acceleration. It is not a function of time. You don't see t anywhere there. So we can use the second equation. We'll go ahead and use both to show we get the same answer. So we'll start with the first equation, and we'll use r instead of x. Okay, you can do that because we're just doing a different position. So r at t equals 0, we plug 0 in wherever you see time, and you get the position vector is 0.60 times I hat. We then find the position at time equals 2, and in this case we substitute in t equals 2, and our position vector is 1.8 I plus j. So to find our average velocity now, we take, and you know what, let's erase this. Okay. And what we're going to take is this term here minus this term. So here we are, and this is where I said we're going to be using the r vector instead of x because we're working in 2 dimensions. We have 1.8 I plus j minus 0.60 I, and we get our average velocity as 0.6 I plus 0.5 j. Now we'll use the second equation, it's this equation right here, and we'll plug in, we have to find v at time equals 0, and that's 0.50 j. V at time equals 2 is 1.2 I hat plus 0.50 j hat. And here's what we're doing, and then we substitute in our values, and we get the average velocity is 0.6 I hat plus 0.50 j hat, just like we got with the first equation, so that's very good. So the magnitude is the square root of vx squared plus vy squared, and we get 0.78 meters per second. And the angle is the inverse tan of 0.50 over 0.6, and we get 40 degrees. So that is the magnitude and direction of the average velocity vector between those 2 points. We need to find the magnitude and direction of the instantaneous velocity of the marker at 3 times. Here, 0, 2, and 4. Instantaneous means we take the derivative. So velocity is dr dt. We take the derivative of 0.60 plus 0.30 t squared I hat plus 0.50 t j hat, and we come up with this value here. And now it's just a question of substituting in the different times, 0, 2, and 4, and we come up with these three vectors here for the 3 times. But again, that's not what we want as a final answer. We need the magnitude and direction of that. So we use what we have over here, and we'll do that on the next slide. This slide is terribly busy, but we're doing the same thing 3 times in a row. So we'll take the easiest one first. At time is equal to 0. Here is our expression. So the magnitude of that is just going to be 0.50 because there is no I component, I hat component. And if it's just in the y direction, what angle are we making? Well, if we have our coordinate system like this, the vector's in this direction. It's purely in the j direction, the y-axis. 2 and 4, a little more tricky. We solve for vx and vy. Here's the vx term, here's the vy. Put them in. Fooled you with that arrow there. To find the magnitude, we get 1.3 meters per second. Do the inverse tan, and we get 23 degrees. And then again, we do the same thing for t equals 4. And once you've checked this to make sure you got the same answers with your calculations, we can move on. Find the magnitude and direction of the instantaneous acceleration at t equals 4 seconds. Does the acceleration change with time? Well, you know what? We actually did this earlier when we were trying to see if we could use both of the average velocity equations, because we could use v0 plus vf over 2 if we had a constant acceleration. But we'll repeat it. So here's our velocity. That's the first derivative of position. You get this. Take another derivative to find acceleration, and you just get 0.6i. So the acceleration is constant. Again, we found that earlier, but we'll do it again here. It does not depend on time. It has a magnitude of 0.6, and because it's just in the I hat direction, if we were to draw a coordinate system, it's just like this. It makes a 0-degree angle with the x-axis. It's directed along the x-axis. Sketch the marker's trajectory from t equals 0 to t equals 5 seconds. First, let's take a step back. What does the College Board mean when they say sketch on their exam? Well, here's a direct quote from their website. Sketch means to draw a graph that illustrates key trends in a particular relationship, such as slope, curvature, intercepts, or asymptotes. Numerical scaling or specific data points are not required. So what we're going to do, we'll do a little extra. We are going to show numerical scaling, just so you can know how to do the physics here. And just realize it's not required by the APC exam. And then we'll give tips for sketching the graph. The position vector is a parametric equation, as r, which consists of x and y coordinates, is a function of an independent variable, or parameter, called t. For more info on this, please check in your calculus class, and I'm sure the teacher will be glad to help. And to graph this, you can either use your graphing calculator, which is allowed by the College Board, or if you're doing it at home or at school, there's a wonderful online resource. I'm sure there are other ones, but this is the one I use, graph-free.com. So the graphs you see in this presentation are products of graph-free.com. The first thing we have to do is determine the scale of the graph. We have to know what our min and max values of x and y are because, why is that? Well, we'll be graphing x and y. Now they depend on t, so what we're going to do is find out what the position is at time is equal to 0, and that's this, and the position at time is equal to 5, and see what values of x and y they have. So r at t equals 0 is equal to 0.60i. So we know that the lowest value of x will be 0.6. Now let's go, and what's the lowest value of y? Well, there is none, so that would be 0. So we've identified these terms. Now the position at t equals 5 will be 8.1i plus 2.5j. So the 8.1 gives us the max for x, and the 2.5 gives us the max value for y. Inputting our criteria into graph-free.com, the graph is drawn as so. And we can see our scale, x ranges from 0.6 to 8.1, so that looks good, that's the x-axis, and y goes from 0 to 2.5, and you see it's kind of got a parabolic shape here. So that's what graphfree.com gave us, and I'm sure if you put this on your calculator you'd get the same thing. But of course you had to set the scale right based on your time equals 0 to time equals 5 seconds. So now let's try and sketch it without any aid from programs or calculators. Well, since we're graphing from 0 to 5 seconds, let's make a little table. And we will have the table as a function of t. And we're going to have 0, 1, 2, 3, 4, and 5. And then we'll find out what x and y is for each one of those. Okay, so x will be the component of I hat, and y will be the component of j hat. So we go ahead and put those numbers in, and we get these, we fill out x and y. And then we'll just plot the points. We expect there'll be a parabolic nature to the graph y because of the t squared here. So I think we're going to plot it on the next slide. And here we go. We plot the points, and you can see the points, right? There's 1, there's 2, so we have our points. And then we certainly do not draw a straight line through them or go for a line of best fit because we expect somewhat of a parabolic shape. So we just draw in kind of a smooth curve like we've done over there. So for the APC exam, you wouldn't have to have any of these numbers. Okay, you would just have to have the curve. But just to make sure, as long as you figured out the x and y values, I would go ahead and put that in. And of course, make sure that you title your graph, marker position, and you label the axes, x-axis, y-axis, and that actually is the x and y position of the marker, and ensure you put in units. And finally, this problem seems as if it's gone on forever, right? We want to find the angle between the displacement and acceleration vectors at t equals 4 seconds. So we take our position vector here, we substitute in 4 for the time, and we find out that the position vector is 5.4i plus 2j hat, and then we have our acceleration vector over here. Now a clever way to do this is go to our vector dot product. Why? Because that will give you the angle between two vectors, and all you have to calculate is the dot product and the magnitude of each vector. So let's see what we have. Here's our dot product. A dot r is the magnitude of A times the magnitude of r, cosine theta. We go ahead and solve that for theta, and that's this. And let's see, A dot r is on the top, and what we get there is we have 0.6i dot 5.4i. That gives you 3.24. 0.6i dot j is 0. Those are perpendicular vectors. Their dot product is 0. Then we do the magnitude of the two vectors on the bottom. The acceleration, of course, is just 0.6 because it's just 0.6i. And then for the position vector, we take the square root of the square of the x term and the y term, put the numbers in, and we get 21 degrees.